Okay, class. Let's look now at a phenomenon for waves, and that is called diffraction. And one way to understand this is imagine that you have water, and then these are water waves, right? Water waves that are coming to a wall, and imagine that that wall has an aperture here. So what you're going to see is that once that this wave, this planar wave, reach the wall, some of the water is going to go through the hole, and what you're going to see in the other side is these spherical waves. This is called diffraction. This is a known effect called diffraction, and this happens to all waves. And the condition for this effect to happen is that this length here, the length of this aperture, have to be about the same size of this wavelength, the wavelength of the wave. If this wavelength is about the same size of this, then you get diffraction. Let's look at a quick question here. You have two rocks, and then you simultaneously drop them into a pond. And so then you get these ripples, and they are shown there. And this is the wavelength from blue line to blue line, and this from green line to green line is also a wavelength. So at this point right here, what type of interference you get? Is it constructive or destructive or somewhere in between? Take a minute and think about the distance from this point to this point and from this point to this point in terms of the wavelength. Okay, to answer that question is, well, you see this point is 1.5 wavelengths away from the source. And this point here is 2.5 wavelengths away from the source. So therefore that is going to add to a maximum here because, well, you get exactly the maximum here from this wave and from this wave. So it's a constructive interference. Now, when you see light going through an aperture, like this door here, then you don't see a diffraction. And then you must, from there, if you think that light is a wave, then the conclusion is that the wavelength must be way smaller than this length from here to here. So, and however, if you shine light, like here, you have a laser going through an aperture, and this aperture is about 0.1 millimeter wide. And then you look at a screen at what gets projected after the light goes through this aperture. What you're going to see is these fringes. So this suggests that, well, light is behaving like a wave, and also that the wavelength should be around this much, this 0.1 millimeters. So we have models of light. So we have the wave model, and under many circumstances, light exhibits the same behavior as sound or water waves. So we use the wave optics to study light when it behaves like a wave. Then we have a ray model, and ray model happens when light behaves like particles in a way, it travels in a straight line. The model that we use is ray optics. And finally, we have a photon model, which is the one that we use in quantum mechanics and in the quantum world. And in that model, life is made of photons, which are particle-like particles, and they have particle-like properties. So in this week and the next one, we are going to concentrate on the wave model and the ray model of light. So let's start by looking at Young's double slit experiment. In there we have light going through two apertures. So after light goes to the true aperture through the two apertures, then you're going to have these two waves spreading, right? And then what you're going to see on the screen here is this diffraction pattern. So this is a very famous experiment, and what we are going to do is use what we know about interference to try to understand these patterns. So remember, this is a top view of the same experiment. So you have here light, and these are planar waves that are coming this way. This is lambda. The distance between this point and this point is the wavelength. And then after it passes through the aperture, then you're going to have this spread out from the two apertures, right? And you can see that along these lines here is where you're going to get these maximums. And these maximums are going to be labeled. You label them with integers, this being 0, which is a maximum, and then going to 1, 2, and 3. So, and the idea is to predict, what we want to do is predict the location of these maximums. To do that, if we take a look at the top view, then we have the following trigonometry properties, right? So here is our double slit, and it's very small here. And then this distance from here to the screen, we're going to call that L. And then this angle here, theta, is going to be an angle that gives you, this is the location of the maximum that you want here at P. And then you have this angle theta, right? So now you have L, you have the location of the maximum that you want, and this distance here, this distance is L tangent of theta, right? That is this distance. So now that we understand the trigonometry, let's look at a zoom of this here. And what we are going to assume is that this distance L is way much bigger than the separation between the two slits. So if that is the case, then light coming from this and light coming from these apertures, they are both pretty much parallel. And then all we need to do to calculate the difference in the phase difference is to get this distance here, from here to here. And this distance is what? Is delta r, which are going, that's what we're going to call this distance, is d sine theta. This theta is the same theta here, which is also the same theta here. Okay, so delta r is d sine theta, and that is the difference in path length. This is the difference. This way, the wave coming from this hole travels less than the wave coming from this hole. The extra length, this is the extra length that a wave coming from this hole travels to get to this point here, P. So delta r is d sine theta, and then the maximum is going to occur when we get that delta r is equal to a multiple of the wavelength. Delta r is m times lambda. So we can put that condition into an equation, right? So then if we put that condition into an equation, that delta r is equal to m times delta, and delta r is d sine theta. And also we are going to use the property that we are going to have very small angles. So we can write that the sine of the angle is pretty much equal to the angle, right? So then you get that delta m is equal to m lambda over d. And finally, from here, and using this relation here, L sine theta and L, this is the position of the maximum here. So you can get this expression for the position of the M maximum of M fringe in your diffraction pattern, and that is M lambda L divided by D. So in a following experiment next week, we are going to be working on this. And for now, this is, oh, thank you.